Okay, so we're recording just a very short video here. So this is kind of like a summary of the analysis of damped harmonic oscillators. So if you go to page 150 in your manual, we'll just talk this through. So this is the equation of motion for a damped harmonic oscillator. If you take these two away from both sides, you end up with mass times acceleration is equal to the sum of the forces, and you've got a damping force, lambda times velocity, and a Hooke's, or minus lambda times velocity, and a Hooke's force minus k times the displacement. So this is the equation of a damped harmonic oscillator, mass times acceleration, this is damping and this is the spring force. Now the full analysis up to page 150 is very heavy. What it basically boils down to is that the full analysis, kind of the outer box analysis as such, is that you've got these two parameters here. Now omega 0 can be thought of in various different ways, but here you want to just think about it as a parameter related to the spring force, and gamma is a parameter related to the damping. And basically these are the two things that you need to compare to say, to predict, is it going to be under damping, over damping, or critical damping. Now I've got small damping here. Now that's the same as under. Large is the same as over, and critical is, well, critical is critical. So this is the damping and this is kind of the spring. So when the damping thing here is bigger than the spring, then you're overdamped, etc. So this is one way of analyzing these, but there's others. So first of all, the differential equation as it's written in your exam paper nearly always will not have a mass term here. It'll already be divided out. If there is a 2 here, by the way, it's not a bad idea to divide everything both sides by 2 in the first place. So rather than kind of this big analysis, which you could actually do, what I'm getting at here is there's be a 1 mark or 2 mark question on a normal year where it's like, is it small damping, is it under damped, over damped, etc. And you need to be able to analyze it, and this is not the way. The better way is as follows. Solve your problem, okay, and then depending on what happens, you can say what type of damping it is. So basically the answer here I'm saying is look at the solution to say what type of damping you have. Okay, so if you do the first 3 steps of the Laplace transform, you get down to here, and this isn't in the tables, so you want to write it as a sum of simple things that is in the tables. And doing that is called doing the partial fraction expansion. And so what you have to do is you have to factorize the bottom. And there's 3 different things that can happen when you factorize the bottom. The first is actually that, first of all, you won't be able to factorize it using the method I did in class. And then if you look towards the minus b formula, if you look at the b squared minus 4ac, if that turns out to be negative, there are no real roots, no real factors, and so what you have to do in that case is complete the square. And for me here, I've got a k, but k is the same as omega here. K is just an old tables I used to use. And if you mess around with this, eventually you get shifted cosines and shifted sines, and again here, so you bring back the cos and it's shifted, so you multiply by, these are exponential shifts. And this thing, if it's got sines and cosines, it's oscillations, and because it's multiplied by exponential decay, it's oscillations that are getting smaller and smaller and smaller. And that means if there was no door frame, they'd oscillate. If there is a door frame, they'd slam. This is underdamped. The next possibility is if you factorize it and you get 2 different factors, 2 rule 1s, and then when you send them back, you get 2 different exponentials. One of them will be slow and one of them will be fast. So essentially what you're talking about now is that displacement will go towards 0 quickly, and then it'll go very, very slowly. This looks the same as critical, but that it closes quickly and then slowly, and that's what overdamped is. And then the other possibility is that you get a rule 2 basically, and in that case this one comes back normally, but this is a shifted 1 over s squared, and because it's shifted it'll be multiplied by e to the minus alpha t, and here you've got the 2 same speeds, and this is critical damping. So the conclusion basically is, if you're asked to analyze the damped harmonic oscillator, say what type of damping it is, etc. So the first thing is, rather than maybe looking at the thing I said on the previous page, which is I'm saying is not actually recommended, probably the best thing to do is to solve the differential equation and just look at the solution. If you've got two exponentials of the same speed, it's critical. Different speed, it's overdamped. And if you have oscillations, it's underdamped. The alternative to this is look at b squared minus 4ac. If that's over 0, that's going to correspond to overdamping. If you read this, under 0, underdamping, equal to 0 is critical damping. So these are your options. So that's all the lectures for this week, which I think, and I'm a little bit lost, but I'm fairly sure it's week 9.